Thank you very much, and thank you very much for the award last year as well. That was wonderful to get. Of course, sort of a travelling lectureship turned into a bit of a Zoom lectureship, but that was still very good to get sort of my research around, which was really nice. So yeah, this is it. This is the research I was and will be presenting, and it's looking at the inorganic carbon budgets of a high Arctic watershed. And if you want to get in touch, my email is here, as well as Twitter and Instagram. I'd really like to thank Mel, without which like none of this work would ever happen, but also all of my collaborators as well, who really helped with sort of the intellectual knowledge and building models, and occasionally paid for the odd isotope measurement or two. So thank you to them. I want to start by showing you the region where me and Mel have been working for the last few years, since 2018. This is the Zackenberg River in Greenland. As you can see, it's a really beautiful place, but by looking at the landscape, you might not think that it would play such an important role in the inorganic global carbon cycle. The landscape is pretty barren. There's not many plants. It's underlain with continuous permafrost, and there's an average temperature of about -9 degrees. So you'd be right, considering the traditional global carbon cycle, the silicate weathering rates are very slow, and they are low. What I want to show you today is that actually we need to expand our view of the carbon cycle and the processes that govern it over these long-term timescales, and move on to more of an emerging view of the carbon cycle, and thus the sulfuric acid weathering. But in order to put that in context, I want to kick off with the traditional view of the carbon cycle. So this is, I have quite a few figures actually taken from this recent paper, which is excellent, by Bob Hilton and Josh West, which I recommend that you read. But essentially this shows how the textbook or traditional view of how we look at how carbon cycles, the inorganic carbon cycle on geological timescales. So we have carbon dioxide in the atmosphere, and also dissolved within soils, which can dissolve into water to create a very weak acid, carbonic acid. And this can weather both silicate rocks and carbonate rocks on the Earth's surface. And with silicate weathering, we draw down one molecule of CO2, which is eventually locked up as calcium carbonate in the oceans. The emerging view, so this traditionally only looks at inorganic carbon, so calcium carbonate, and only the action of carbonic acid. And the emerging view starts to take into account different acidity sources, such as sulfuric acid, but also the organic carbon impact on the long-term carbon cycle. So here we've got in the green boxes, the rock organic carbon cycle, and also again in the blue, we have the inorganic carbon cycle. And we need to think, how big are these fluxes, and are they big enough to offset the traditional way we look at silicate weathering? And the one I want to focus on today is actually the sulfuric acid weathering of carbonate rocks. So sulfuric acid can be formed in different ways, which I'll talk about later. But essentially, if it reacts with a carbonate rock, it can produce an instantaneous release of CO2 gas, which on the long term has the potential to counteract or even make a particular region CO2 neutral with the amount of CO2 that's taken down via silicate weathering. So for sulfuric acid, weathering in particular, it's still a nuanced reaction to look at, but it's not the first time, certainly in this talk, that it's been looked at. And quite a few studies have been looking at this new role of acidity source. And I thought I'd highlight a few here. And what's really interesting about these three studies is that they all find that physical erosion is positively correlated with the rates of sulfuric acid weathering. So just to highlight what these studies have shown, this is the Mackenzie River Basin in Canada, and it shows that physical erosion rates are positively correlated with sulfide oxidation rates. And it's this reaction, sulfide oxidation, that produces sulfuric acid. This one, after Mark Torres, they looked at the Amazon River Basin from mountainous environments here in purple, all the way down to mountain fronts and floodplains. And they find that proportion of weathering by sulfuric acid relative to carbonic acid is much, much higher in high erosive regions, such as mountains. And then again, this is after Bob Hilton and Josh West, and they took some of the biggest rivers in the world, looked at their overall net CO2 budgets, and found that carbonate weathering by sulfuric acid and this is tons of carbon per kilometre squared per year, is positively correlated to these different rivers throughout the world with suspended sediment yield. Again, this is linking sulfuric acid weathering with physical erosion. So once we start to take these new reactions into account, we can start to have sort of a little look at how we think the net carbon sources might be balanced in different regions. So this is a schematic of the CO2 sources and sinks by weathering in different environments. And the ones I want to focus on here are the inorganic carbon flux. So this blue here is the CO2 drawdown from silicate weathering, and the orange is the CO2 release from the sulfuric acid weathering of carbonate rocks. As you can see, there's different patterns as to draw down and release, depending on you've got a hot and wet climate or a cool climate, the rates of erosion, so H here being high and L being low, and also types of bedrock. So sedimentary rocks contain lots of sulfides, and so you'd imagine that the sulfuric acid rate is higher. The arrow here also shows that this is the net release. So by taking into account these other reactions, it can shift our calculations of the long-term CO2 fluxes, which are very dependent on climate, rock type, and erosion rate. And in particular, catchments with high erosion rates, such as in the mountains, these reactions can be kinetically limited, whereas in regions of low erosion rates, reactions can be supply limited. And this will have an effect on the type of mineral acid reactions that can occur. Therefore, the roles of climate and erosion on the carbon cycle cannot be understood by considering just silicate weathering in isolation. So taking that bit of knowledge and applying it to the Arctic, which is where me and Mel like to work, when we look at the Arctic, sort of in the grand scale of things, for the global inorganic carbon cycle, the Arctic and also to some extent the Antarctic are typically considered to be relatively inactive, as the temperatures required for substantial mineral weathering are very low. However, since baseline measurements began in the early 1990s, the sediment export from the Arctic has increased by over 50%, and the total amount of sediment is almost the same as the entire African continent. So the sediments that are being released into the ocean are typically very fresh and unweathered. They are finely ground sediments with a large surface area to volume area. And therefore, the potential limitation of low Arctic temperatures on weathering reactions could be overcome by the large supply of sediment, which does contain highly reactive minerals such as sulfides and carbonates. So our hypothesis was, or what our research seeks to find, is a potential link between physical erosive processes in the Arctic, such as permafrost degradation, glacial retreat, great glacial grinding, and glacial outburst flood events, with the amount of sulfide mineral oxidation and the potential for net CO2 release to the atmosphere. And the ideal place to do this, we think, is in the high Arctic watershed of the Zackenberg, which is in the background here and is, where's my little cursor, in the northeast of Greenland, in the Greenlandic National Park, and I'll show you why. So again, this is the Zackenberg River, which flows through here. It integrates a very small a relatively small catchment area of about 514 kilometers squared. There is a fault which runs north to south, which separates the two major geological units. There are to the east Jurassic and Cretaceous sediments, and to the west Paleoproterozoic basement rocks. The region is underlain with continuous permafrost, which I think thaws up to a maximum of about a meter each year. And because of that, there's also thermokarst collapse and riverbank collapse because of that permafrost. There is a glacier off to the west, which is not actually connected to the main Greenland ice sheet, but is a smaller glacier. And this is the main water source to the region apart from snowmelt and permafrost thaw. And additionally, this glacier usually every year undergoes a big glacial outburst flood event, which means about 50 to 60% of the catchment's freshwater and sediment are delivered in about 48 hours, so a huge erosive event. So we have the annual Gloph event. We also have up to the east, highly incised and low-lying rivers. Again, so that gives us a variation in slope. So we can actually look and measure, quantify a variety of different types of hydrological regimes with variations in geology, slope, erosional forces such as glaciers, permafrosts, and see how these are linked or interplay with specific mineral acid reactions. So this is the Zackenberg Bridge, which integrates the contributions from the entire catchment. What's very useful about this bridge is not just the access and not having to wade across yet another freezing cold river to access a sample site, but since 1996, a monitoring station was set up here where, amongst many other things, the site has consistently measured discharge and dissolved chemistry, as well as suspended sediment flux on twice daily timescale. So altogether, this means we can look at the spot sampling scale to see how different regions of the catchment contribute to different mineral and acidity sources, but also how the region has varied over the last 20 years or so. So since 2017, as I said, myself and Mel have been visiting this site in order to look at these different mineral acid reactions. We have been lucky enough to go in different seasons, in different years. We take detailed hydrological measurements such as pH, conductivity. We take water samples to quantify the elemental distributions between the solid and liquid phases, so we can determine what minerals are in the catchment and what minerals are weathering. And to determine the acidity sources, we titrate for alkalinity, which is something we can do at the field station. But tracing sulfuric acid is a little bit harder to do from just dissolved river water chemistry. Dissolved sulfur in the river can be from a few different sources, the weathering of sulfate and the weathering of sulfide. Therefore, quantifying CO2 release from sulfuric acid requires the partitioning of the riverine sources of sulfate between its two main end members. This is because the weathering of sulfate does not produce any acidity when the mineral dissolves, whereas weathering of sulfides, such as the oxidative weathering of pyrite, produces acidity when it is oxidized. So we need to determine how much of this sulfate is from this reaction. So to partition the sulfate between the two sources, many studies have looked at the sulfur isotope composition of the water, as shown here. But although the sulfur isotope ratio of sedimentary sulfate, such as gypsum and hydrite, of different ages are very well constrained, the sulfur isotopic composition of sulfide minerals is really very variable. So this does restrict the use of just using sulfur isotopes alone to partition sulfur sources, as there's a large amount of overlap. Therefore, in the model that we use and Katie Relph here developed, we start to look at the oxygen isotopic composition of the sulfate molecule and the coeval water, which has a much larger distribution and much bigger variation between evaporite and pyrite end members. This is because the sulfide-derived sulfate, so here, contains water, which is meteoric water, which has usually come from where the sulfate has been oxidized, so where sulfide has been oxidized, and this measurement of water is actually something that's very, very easy to do in the field. Whereas the sulfate composition, the oxygen isotopic composition of the sulfate molecule will retain the signature of seawater from the time of its deposition. So we can actually partition based on the oxygen isotopic compositions. So if we have an isotopic composition of river water, so this is once it's been corrected for atmospheric inputs such as rain, it must have come from two primary sources, especially in the Arctic where the pollution is next to nil. You might have to worry about that in a much larger river. We know the age of the bedrock that we are draining, so we can constrain the evaporite end member by just looking at the literature as the oxygen retains its signature, as I said, of seawater from the time of deposition, in addition to a small amount of isotopic fractionation. And then we can use a binary mixing model to work out the amount that's come from pyrite. Since we know the isotopic composition of the coeval water, where we assume the sulfur has been formed, and we know the isotopic composition of atmosphere, we can quantify how much, we can quantify the isotopic composition of the potential pyrite molecule, of the sulfate that has come from the pyrite. And the water from the sulfate that's derived from oxidative weathering pyrite is a function of the amount of atmospheric oxygen, which I think varies up to 30% maximum, versus the water from which it's precipitated, the isotopic compositions of the water and the oxygen, and also the fractionation factors, because these will determine, because there's a fractionation on incorporation of either oxygen into water or from water into sulfate. I'll hurry up a bit because I see that the time is going. So essentially we can do a Monte Carlo simulation to work out the errors associated with this. What we find is, so this is the Zackenberg River and the tributaries here, all in the same color, I'm afraid. But if you just have a look at these pentagons, the orange and the red, from 2 different years, we find that the model results show that 85 to 100% of all the sulfate we're measuring from the Zackenberg River has actually come from the oxidative weathering of pyrite, which pretty much is saying our sulfur source is almost completely from sulfuric acid. We found there were 2 sources because there were slight isotopic differences between the 2. These were draining the Proterozoic basement and these were draining the sedimentary basement. If we want to look at how the mineral acid reactions vary, we can actually do this using a model framework that was based by Torres et al. So this graph gives us the ability to look at the variation in acidity source versus the variation in rock source. So FCarb, 1 means all the rock sources from carbonates and 0 means all the rock sources from silicates. And again, with the acidity source, 1 is sulfuric acid, 0 is carbonic acid. Unfortunately enough, there's actually a line we can draw here between CO2 release in the long term and the short term. So these are our samples from the Zackenberg River, and they pretty much all lie in this release. So high amount of carbonate weathering and a small amount of sulfuric acid weathering, which is resulting in a release of CO2 long term. So these were the results from our spot sampling. But what we can do is, because there's a database going back 20 years, we can take the compositions from the Zackenberg bridge samples, which is where the long-term monitoring has been done. And we can go back over 20 years and see how all these different mineral acid reactions have varied over the last 2 decades. And whilst there is some variation, and I don't have the time in this talk to go into all of that variation, we can see that predominantly all of these reactions are mostly in the CO2 release. But the size of the dot represents the discharge on the day and the color represents the day of the year. Because I can't talk about that all today, I'm going to show you the results of what happens when we look at it on a yearly basis. So these are the different years. If we look at just the traditional flux of silicate weathering, we see that indeed the whole region is just CO2 drawdown. But if we actually take into account the sulfuric acid weathering of carbonates, and this is the amount of carbon that's being released from these reactions, we see that it completely outweighs the amount of CO2 drawdown from silicate weathering by carbonic acid. And if we put the arrows on here, we can see the net amount of CO2 that's released. So our original hypothesis was, is this related to erosion rate? And the answer is somewhat. So next to the long-term CO2 effect, I've done the erosion rate and I've correlated the 2 here. And what we see is some years, for example, 2015, we have a high amount of CO2 release and a high erosion rate. But then in other years, for example, 2013, we have a high CO2 release, but we don't have much high erosion rate. And so they're not completely related on a one-to-one scale. So there's something else going on here apart from just erosion rate. And I think the important thing here is that lithology and hydrology are key. So of course, where we have the granitic basement, we have a low concentration of sulfate from pyrite, whereas in the sedimentary region, we have a high concentration of sulfate from pyrite, even though the rivers are smaller. So if we were to look at a typical discharge, suspended sediment on a yearly basis, I've taken here 2011, we can see the variation in discharge in the blue and the variation in sediment export in orange. And whilst we have a GLOF event, which has low amounts of sulfate, which results but also high amounts of sediment, this is coming from the granitic basement, whereas later in the year, we have these rain events, which is getting rid of lots of the sediment from the sedimentary basement, which is causing this additional release of carbonic acid silicate weathering. So in the grand scheme of things, how large is this flux? I've put here some of the largest rivers in the world where the overall net flux has been quantified. And the Zackenberg River is really, really tiny compared to some of the largest rivers in the world, but perhaps it's fairer just to compare them against the Arctic rivers. So this is where the Zackenberg River sits. There is an overall flux of 6 tons of carbon per kilometer squared per year. Which is, similar to the Mackenzie, but what's really interesting is if you compare the sizes of the catchment, so 1.8 million kilometers squared versus 512. So it really shows you that this small river can have quite a large impact. And I think before I run out of time, this is the summary. So we've looked at the different isotopic compositions. We've done the spot sampling record, and we've also done a long-term record, which have all shown that the impact of sulfuric acid weathering is very strong in the Arctic. And maybe there's the potential for a very small positive climate feedback loop. We have CO2, temperatures rise, we get the receding of glaciers exposing new fresh sediment. This sediment, depending on the type of lithology, can potentially contain lots of carbonate and sulfides, which can then result in a net positive CO2 flux. And I will finish there. Thank you. And sorry for running over.
Us on time. Thank you, Emily. Okay, interesting stuff. Really cool looking fieldwork as well. Very envious. There are a couple of questions that have come in, one from Gav Frost and one from Phil Pogge. Perhaps if you get a chance during the session, you could answer in the chat box.
Of course, yes, yeah.
That would be great. Do it to everybody, and then we can all enjoy the answer at the same time.
Okay, that's fine.
Brilliant. Thank you very much, Emily. And now